Hello. In this series of videos, we are going to look at the special relativity theory, and we are going to derive the famous equation, perhaps the most famous equation of all, E equals mc². Before starting though, I need to remind you that special relativity applies only to what are called inertial reference frames. And an inertial reference frame is quite simply a frame which is not accelerating. It is either stationary or it is moving at constant velocity, but it is not accelerating. Neither is it going round a curve or going round in a circle. Even if it is going at constant speed around a circle, it is accelerating because it will have a centripetal acceleration. So it must be travelling in a straight line at a constant velocity in order for it to be an inertial reference frame. If it is accelerating, then you have to move on to the general theory of relativity. Let us consider an inertial frame called S. If you like, you can imagine this as a spaceship in outer space. And there is a second frame of reference called S prime. All we can tell is that S prime is moving relative to S at a velocity v. There is no experiment that you can do to demonstrate whether S prime is moving to the right at velocity v, or S is moving to the left at velocity v, or maybe S prime is moving to the right and S is moving to the left at a combined velocity of v. All physics works exactly the same if you are moving at constant velocity as if you were standing still. What we're going to do is to put an aerial on top of the S frame and a dangling wire underneath the S prime frame, such that when S prime passes S, the dangling wire touches the aerial, contact is made, and two clocks, one on board each frame, is synchronized. They both start from t equals 0, and we might imagine that they will forevermore be synchronized. But as we shall discover, that is not true. After a short time, there is a light flash, some distance away. People on both frames of reference are able to use their frames of reference to gauge the distance that that light flash is away from them. S says that the light flashed when it was x away and when the time on the clock measured t. S prime, on the other hand, says that the light flashed when it was x prime away and when the time on the clock measured t prime. Now I think you can see fairly easily that x equals x prime plus this distance, which represents the separation of S and S prime. But what is that distance? Well, the relative speed is speed v, and the time that has elapsed is, depending on whether you're measuring it on one clock or the other, t or t prime. So the distance will be the velocity times the time, vt or vt prime. So now we can say that x is x prime plus vt prime, or if you prefer, x prime is x minus vt. All of that sounds fairly straightforward. Now I need to introduce you to an experiment that was conducted by Michelson and Morley in the late 1800s that caused all of the understanding of Newtonian physics to be stood on its head. I shan't describe precisely how Michelson and Morley did their experiment. I'm going to give it to you in a way that I think is more easy to understand. Before we look at their experiment, I want you to imagine that there is a train travelling along in a straight line at 30 miles an hour. You are standing on that train and you have a ball in your hand. You roll the ball along the corridor of the train in the direction in which the train is travelling, and the ball goes at 20 miles an hour relative to you. There is a person standing on the platform who can see the ball on the train, and you ask him to measure the speed of the ball. He will say that the speed is 50 miles an hour. That's the 30 miles an hour of the train plus the 20 miles an hour of the ball. Now you turn round and face the other way. And again, you roll the ball at 20 miles an hour along the corridor of the train, but this time in the opposite direction to the way the train is moving. Now you say to the person on the platform, what speed is the ball travelling? And he will say it is still travelling at 10 miles an hour in the direction of the train, because the train is going at 30 miles an hour, the ball is going backwards at 20 miles an hour, and the net effect is 30 minus 20, which is 10 miles an hour in the direction of the train. So far, so good. But now let's imagine that instead of rolling a ball, we shine a torch. And that, in essence, is what Michelson and Morley did. Obviously, they didn't do it on board a train, because that would not have been very practical. But in principle, this is what they did. They took a torch and shone it in the direction of the train. And they know that the speed of light relative to them is c, which is actually approximately 3 times 10 to the 8 meters per second. Then they said to the man on the platform, what speed do you measure for light? And of course they're expecting him to say, it is c plus 30 miles an hour. But the man on the platform simply responded, I also measure the speed of light as c, 3 times 10 to the 8th meters per second. And then they turned round and pointed the torch the other way and said to the man on the platform, what speed do you get? And he responded, I get c, 3 times 10 to the 8th meters per second. Surely you should get c minus 30. No. The speed of light, Michelson and Morley concluded, is the same irrespective of the speed of the source of the light or the speed of the observer of the light. And that clearly is counterintuitive. It's completely different to the situation when the ball was rolled along the surface of the train. Somehow we have to explain why that happened. Well, one of the things that you could do is to say that the people measuring the speed have measured it incorrectly. You could, for example, say that since speed is distance divided by time, that the people measuring that speed either are using an incorrect ruler to measure the distance, or an incorrect clock to measure the time, or maybe a bit of both. So let's go back to our 2 frames. And what we're going to do is we're going to arrange that when S prime passes S, not only will this cause the clocks to synchronize, but it will also send a signal to a far distant light and switch it on. Of course, when the light actually appears, S and S prime will be in this position. Both of them are fully entitled to say that they are stationary and that the other one is moving. So S will say, well, the light travelled a distance x in time t, measured on my clock, and therefore c is x divided by t. S prime is entitled to say, the light travelled a distance x primed in a time t primed, and therefore the speed of light is x prime divided by t primed. But we know from Michelson and Morley that c is constant, no matter who is measuring it. Since x and x prime are different, that suggests that t and t prime cannot be the same.